Going from drones and delivery on Earth, we're going to talk about drones flying in on the moons of Saturn and Titan specifically. So we're very pleased to have Jack Langelaan come here, and he's a professor at the Department of Aerospace Engineering at Penn State University. His research focuses on path planning, control, and data fusion, especially applied to navigation, obstacle avoidance, and long-range flight of small uninhabited aircraft. In 2011, he was the leader of the Team Pipistrel USA.com, the winner of the NASA Cafe Green Flight Challenge with a Taurus G4 aircraft. In 2018, he led a team of undergraduate students in the design of the Blue Sparrow, a small personal air vehicle that was a phase one winner of the Go Fly competition. His current project include autonomous shipboard landing, autonomous multi-lift, and Dragonfly, an upcoming NASA mission that will explore Saturn's moon Titan. That's what you're going to hear about via autonomous rotorcraft. And so Jack teaches aircraft design, dynamics and control, and aeronautics at Penn State University. He received his PhD in aeronautics and astronautics from Stanford University in 2006, in the same lab that Sarah graduated from. He received a Master's of Science in Aeronautics and Astronautics from the University of Washington, and a Bachelor of Science in Engineering Physics from Queen's University. He spent 5 years working as an engineer at Bombardier Aerospace, primarily on the Q400 turboprop Global Express business jet and the RJ700 regional jet. So thank you, Jack, for being here today. I really look forward to this talk.
All right, thanks, Sherman. I'll share my screen and we'll get going. All right, so hopefully everyone can see the correct screen, which is the presentation mode and everything. So thanks, Sherman. It's great to at least virtually be back at Stanford for a little bit. It was a great place to be for several years. And there is going to be no GPS in this particular talk because there's no GPS on Titan. And unfortunately, I can only give kind of overview stuff because a lot of this mission is still under development. And then over the next several years, you'll see more and more detailed papers come out in sort of the technical literature. And so know that what I'm talking about now is sort of overview level stuff. And a lot of it, anytime I show numbers for anything, then that actually dates back to the sort of phase A and pre-phase A parts of this project. Obviously, I'm not the only person working on this. Johns Hopkins Applied Physics Lab is the lead institution, and there's 4 of us at Penn State that are working on this. And our job at Penn State is really the rotorcraft side of things. So that means the aerodynamics, aeromechanics, flight performance, and maybe a little bit of control for the flight vehicle. So Dragonfly is the NASA New Frontiers 4 mission. I'm just mentioning that because the New Frontiers 3 mission is OSIRIS-REx, and they've just managed to extremely successfully pull some materials off asteroid Bennu, right? And so Dragonfly is the 4th New Frontiers mission that NASA is launching.
Jack, we can't see your screen yet, so you're sharing. Okay.
It's telling me that I'm sharing screen. Oh no, I didn't say share. Never mind. There we go. Sherman, thank you for. Okay, hopefully you can see my screen now.
We can.
Okay, good. Sorry about that, everyone. Okay, so anyway, there's nothing important that happened the first 30 seconds of the talk anyway. So, all right. So in addition to its ring, Saturn has 62 moons. The largest of these is Titan. And it was discovered by the Dutch astronomer Huygens in 1655. It wasn't until 1944 that we observed the thing that makes Titan unique among moons in the solar system: its thick atmosphere. Titan's atmosphere is roughly 94% nitrogen, 6% methane, and there's actually a methane cycle on Titan that's analogous to the water cycle here on Earth. It rains methane, methane flows in rivers, there's methane lakes and oceans, and then methane evaporates back up into the sky, and then it rains back down again. The atmosphere on Titan is roughly 4.5 times denser than Earth's atmosphere, and it's very cold. It's a little bit under 90 degrees Kelvin at Titan's surface. The other thing that makes Titan a wonderful place from my standpoint as an aircraft person is the fact that gravity is very low. So we've sent many missions to past and to Saturn's system, beginning with Pioneer 11 in 1979, Voyager 1 in 1980, and Voyager 2 in 1981. We have imagery that's been taken from both the Hubble Space Telescope and from the Keck 2 telescope. We've got data that comes from Arecibo radio telescope as well. And of course, the Cassini mission was in orbit in Saturn system from 2004 until 2017. It made 126 close flybys of Titan. In 2005, the Huygens probe was dropped into Titan's atmosphere from the Cassini spacecraft. It came down under a parachute, taking atmospheric measurements on the way down, and it landed on the surface and sent back a bunch of pictures. So we've spent quite a bit of time at Titan already. Cassini got a lot of radar imagery of Titan's surface. The Huygens probe got us atmospheric data and the images like the one that you can see here on the right-hand side. And so we have a lot of information about the moon. But the more we learn, the more we realize what we don't know. And we also realize what we can learn if we actually send the lander to its surface. Right? So we'll get accessibility to complex organic material. There's the Earth-like system of the methane cycle. There's a potential for organics to interact with liquid water near or at the surface, right? And there's the prebiotic chemistry, what the scientists call prebiotic chemistry on Titan, right? So there's all the ingredients of life, but so far as we know, there isn't actually life there yet. And so the idea of going to Titan is we can see what Earth was like before life arose here. Okay. There's potential for exchange between the atmosphere and the interior ocean. There's evidence of cryovolcanoes, right? And so visiting Titan gets us closer to answering these sort of main fundamental questions that we have, right? What is it that makes a planet or a moon habitable? What are the chemical processes that led to the development of life? And has life developed anywhere else on the solar system? So what are we going to do while we're there, right? We want to study the chemical processes and the chemical composition at Titan's surface. We want to look at the meteorology on Titan. There's some really interesting weather that happens there. There's geological feature characterization, seismic studies. So that's looking for kind of cryo earthquakes, Titan quakes, atmospheric profiling during flight, and then also imagery that we can take during flight using both the navigation cameras and the science cameras on board the vehicle. So lots and lots of cool things that we will do both on the ground and while we're in the air flying through Titan. There's a lot of sensors on board the vehicle. They all have cute acronyms, right? So DRAMS, the mass spectrometer, that comes from Goddard Space Flight Center. DRAGONS, that's the gamma ray and neutron spectrometer, that comes from Applied Physics Lab and Goddard Space Flight Center. DRAGMET, that's the meteorology sensor. That's Johns Hopkins Applied Physics Lab. And the Dragon Cam, that's the camera suite that comes from Malin Space Systems. And there's many other contractors and organizations that are involved with various aspects of the vehicle, right? So as with all these sort of big space programs, there are hundreds of people that are involved in the work. So why on earth do we want to fly there, right? Cassini told us where to go and where to look on Titan, and now we have to get there. The geography of Titan is very diverse. Scientists want to obtain surface data from several different types of terrain and from various parts of the planet. Sending lots of landers gets very, very expensive. That would be multiple copies of the same lander with similar instrumentation and sample acquisition systems. So a vehicle that can take one instrument set and transport it to multiple sites opens up many more science targets. So the places that we want to go, there's the dune fields here, right? So this is a Cassini radar image. These show dunes. There are the methane lakes that are on Titan. There are impact craters and cryovolcanoes. And then there's also these river deltas that exist. And these are all the kinds of places that the scientists want to go. Okay? So being able to cover Titan by air massively improves the coverage of the surface of the moon that we can get. So we're going to land here in the little green square. The Selk crater is right there. It's an impact crater. Huygens landed right about here. And so we're actually landing similar latitude, similar longitude, and in fact, at a similar time of year to when the Huygens probe landed. The landing ellipse is roughly here, right? This is roughly 180 kilometers or so from the Selk crater. And here we'll have access to sand, right? So that's sand mixed with organics. There's the interdune materials as well as the materials of the dunes themselves. There's the ejecta blanket from the crater, and then there's the impact melt parts as well. So the traverse distance, like I mentioned, from the landing site to Selk is about 180 kilometers. That's a long way, right? The Mars MERs traversed about 45 kilometers or so in their life, and Curiosity has traversed about 20 kilometers since it landed on Mars. Radar maps actually suggest that there are really strong terrestrial analogs to the Titan terrain available here on Earth, right? So for example, the dune regions on Titan look an awful lot like the dunes in the Namib Desert. We'll be able to use these Earth locations to exercise and validate Dragonfly's navigation systems. And since there's no GPS on Titan, right, we'll be doing a lot of this navigation using a combination of visual navigation, radar systems, and LiDAR. So again, here's our landing ellipse and the Selk crater, which is our eventual target. We'll be landing inside the dune fields. And then the dune spacing is roughly 3 to 4 kilometers. So we'll be able to do the hops over the dunes and make our way towards Selk crater. We've got about 3 years of exploration time in the mission. We'll have more than 70 what we call TSOLs. A TSOL is a Titan day of science operation. One Titan day is equivalent to about 16 Earth days. We'll be traveling a total of about 180 kilometers, and that will let us explore somewhere between 24 and 30 unique landing sites on our way across the Titan, right? So this is sort of another key or clue to the point that it really is helpful for us to have a rotorcraft that can give us aerial mobility on the surface. So let's look at what it is that makes aerial mobility really possible on Titan. The big key is the fact that the density of Titan's atmosphere is 4.5 times Earth density. The gravitational acceleration on Titan is roughly 1/7 that on Earth. And there's a couple of extra things that help us out. Dynamic viscosity is significantly lower on Titan, and combine the dynamic viscosity with the high density, we have a kinematic viscosity that's a factor of a little bit more than 10 lower than the viscosity on Earth, right? So the atmosphere on Titan is a wonderful place for us to go and fly. And then, like I said, combine that with low gravity, right? And rather than needing a wingspan of roughly 15 meters in a hang glider for a human to fly on Titan, you could go and fly with a wingspan of a meter or two, right? So you can almost, but not quite, fly by flapping your wings. One of the folks once checked, and I think terminal velocity of Mary Poppins holding her umbrella on Titan is low enough that you can actually safely touch down just using an umbrella if you're as a human coming down through Titan's atmosphere. It's a little bit chilly to do that, right? But it is kind of technically possible. Okay, so what does Titan's atmosphere and gravity imply for flight? But the main thing that it does is that the power required to hover a rotorcraft on Titan is about 1/40th of the power required to hover a rotorcraft on Earth. Okay, so that's a massive, massive improvement in power required and thus the energy required to fly a mission. Okay, so there's a couple of different ways you can use this, right? Either you go and design a vehicle that can fly an enormous distance, right, because you've got kind of Earth scale rotors on the vehicle, or you design a vehicle that has kind of smaller rotors that you can fit inside the aeroshell that you can put on top of a rocket. And now you've got a vehicle you can actually get to Titan, and then you have sort of Earth-like power requirements on this vehicle. And we'll get into a little bit of the power scaling a little bit further on. So, given that Titan's atmosphere was discovered in 1944, right, we're not the first people to propose a flying mission on Titan. Helicopter missions have been proposed since about year 2000. Airship missions have been proposed since the mid-2000s. Multiple versions of balloons, right? Both hot air balloons and helium-filled balloons have been proposed. A couple of different versions of airplanes for Titan have been proposed. This one down here is called Aviator. The neat thing about Aviator was predicated on the availability of a Stirling cycle radioisotope thermal generator. And this Stirling cycle generator had just enough power that you could maintain constant altitude flight for the airplane, but not enough that you could both communicate with Earth and maintain constant altitude flight. So the mission profile assumed that the aircraft would climb under power until it reached a high altitude and then descend in a glide while transmitting science data back down to Earth, right? And so then repeat this sort of cycle of dolphin type flights. There was a lander that was supposed to go, or was proposed to go, to one of Titan's methane oceans. That's Titan, the Titan Mare Explorer. And then some flagship mission studies that were done between NASA and the European Space Agency combining landers and balloons. of various types. Okay, so multiple proposals for flight vehicles on board Titan. The reason why you really want to have a rotorcraft to do the sorts of missions that we want to do is because we want to be able to do repeated landings, right? There are some winds. Winds on Titan are quite low. Roughly 1 meter per second wind is a very breezy day on Titan. Okay, but if you're trying to touch down a balloon, that becomes really tricky. And it's the ability of a rotorcraft to do precision, repeated takeoffs and landings. That's the thing that makes the rotorcraft really the sort of key capability that allows us to do science missions at multiple geographic sites. So there's many parts in the Dragonfly mission, right? There's the spacecraft side of things. So that's the cruise stage. That's how we get from Earth to Titan. There's the entry vehicle. Okay, and the cruise stage includes various high gain antenna or various antennas to talk to Earth, as well as stabilization. The entry vehicle is the entry, descent, and landing assembly plus the lander. Okay, and I'll kind of go through a little bit later what the EDL cycle looks like for this thing. And then there's the lander itself. Okay, and so here you can see why we call it a lander. And so as an airplane guy, I'm a little, you know, I was calling it the flight vehicle for a long time, but that caused confusion with the spacecraft folks who called their thing a flight vehicle. And this thing really looks a lot like, you know, the Volkswagen Doka bus. And so, yeah, we call it a lander. It flies, but it spends most of its time on the ground doing science missions. It has an MMRTG. This is the multi-mission radioisotope thermal generator, as the same thing as on the Curiosity rover that's on Mars. It puts out, depending on where we are in the mission cycle, something between 100 watts and 70 watts of power. And we use that to charge the flight batteries and to run our science activities. The waste heat from the MMRTG, that maintains the lander temperature. We can do direct to Earth communication through a high gain antenna. That high gain antenna is articulated so it points towards Earth. We also have a low gain antenna so we can send low rate data back down to Earth as well. And there's also these little sort of Mickey Mouse ears that are sitting on here. Those are the panorama cameras. And so we can take pictures of terrain by moving the high gain antenna around. And we can take science measurements both while we're on the surface and in flight. In flight, we'll be doing aerial imaging and atmospheric profiling. While we're on the surface, we've got in here, there's a drill on each leg, and the drill can penetrate the terrain, and it pulls surface materials up into the lander so they can use the instruments on board the vehicle to do the geochemistry there on Titan. So conceptually, the way it works, right, we're going to launch now in 2027. We'll arrive on Titan, depending on the exact, the exact rocket that we get to use. Right now, it's a 6-year flight time, 7-year flight time to get from Earth to Titan. We arrive at Titan. We do a direct entry into Titan's atmosphere. There's a parachute entry and descent phase. And because Titan's atmosphere is so thick, right, this is really not at all like entry and descent into Mars atmosphere. We spend about an hour and a half descending under the parachute through Titan's atmosphere, right? So rather than a couple of minutes of just extreme terror that you get when you're doing a Mars entry, descent, and landing, you got an hour and a half or so of mild anxiety while we're coming down, right? The sort of joke among all of us is that when you take the integral of anxiety over time, it probably works out to about the same number, right? But it's just spread out. When we're about 1.5 kilometers above the surface of Titan, that's when we turn on the ground radar, detect the surface, and we release from the parachute and we become a flight vehicle. And we actually do a powered flight to our first landing site. We touch down, we do science operations, and then we stow everything and fly off to our new science target. Okay. So one of the really tricky things that we have to do is our very first landing in the interdune region on Titan, right? So here's our Cassini radar image. It's roughly 3 kilometers between each one of these dune peaks, okay? And so we've got a fair bit of space in between. The interdune region is known to be very flat. And so the way we come down, we'll do a couple of passes over the interdune region, and then using a combination of cameras and flash LiDAR, we'll be able to find a spot that satisfies both the slope and the surface feature criteria. And so then the onboard landing site detection algorithms will detect a safe landing site and bring us down a safe touchdown on board at Titan's surface. So as you can imagine, we have lots and lots of constraints, right, that go into this. We have to fit on board a launch vehicle. At the beginning of the project, it was going to be an Atlas V with a 4-meter payload fairing. There's been discussions of expanding the size of the payload fairing. We'll see how that works out in the end. Okay. What that means is, how do we design a vehicle that can maximize our net disk area and still fit inside the entry, descent, and landing vehicle that will then fit inside the payload fairing, right? And so the sort of initial thought was, okay, well, the thing has to be a coaxial helicopter. That's where we're going to maximize net disk area. It turns out that that's not true. Okay. If you place your rotors and align the rotors in a way that each rotor forms a chord within the aeroshell, right, then it turns out that you maximize your net disk area by actually building a quad rotor. Okay. And so you gain roughly 30–40% more net disk area if you build yourself a quad rotor than if you were to just do a straight a coaxial helicopter, right? And so the diagram here shows sort of how net disk area varies if you put your rotors in the vehicle like this. Okay. So this is one of these things that, after you kind of go through, okay, it makes total sense. But initially, right, it's somewhat counterintuitive, perhaps, to realize that a multi-rotor actually maximizes net disk area, given the constraints that we had to work with. Okay, so one of the things that we were doing at Penn State was doing the flight performance calculations. And so this, again, this is all sort of phase A stuff, right? That there are now higher order models that we're using to do this work. But we always assume trimmed flight and flight performance. That means balance all of our forces. That includes body drag terms, body lift, and body moments. Aerodynamic lift and moments are now involved as well. We have thrust from the rotors and then gravity, right? And then we go through a bunch of checks to decide if a flight condition is feasible or not, right? Things like, are we likely to be in vortex ring state for a particular flight condition? If yes, then we deem that flight condition infeasible and we try to avoid it. Are we in a state where we're actually generating power from the rotors because we're in a windmill braking state, right? If yes, then we're not doing it. Is the advance ratio, that's the ratio of tip speed to forward flight speed, too high? Okay, if yes, then we're not feasible. And it turns out there are a few things that Titan's thick atmosphere make a little bit more difficult for us. And one of those is actually advance ratio. So at a high advance ratio, right? So high tip speed compared to forward flight speed, then vibrations in a helicopter start to get large. And so we don't want advance ratios to be too high. The fact that Titan's atmosphere is thick pushes you towards a lower tip speed on the rotor, right? And so you play the game there as well. Okay, we calculate the total power required, right? So that's parasite power is the power that comes from dragging this big body with all the science instruments to the air. Induced power, that's the power that the rotor requires to generate lift. Profile power is the power you need to overcome the aerodynamic profile drag of the airfoil on your rotor. And gravity power is what you need to overcome gravity to climb or descend, right? Here in the phase A versions, that was all conditioned on drivetrain efficiencies. Now, of course, we've got higher order models of the efficiencies of power losses and all the components to the whole drivetrain that are involved. Okay. And so, right, the total required power combined with the total energy that we can store on board the battery, of course, ultimately determines whether, how far we can fly in a given charge. Okay. So depending on the mass of the vehicle, right, and the battery capacity, our flight range is a couple of tens of kilometers. Total vehicle mass is still in a bit of flux right now. For reference, right, Mars Curiosity has driven about 20 kilometers since we touched down in 2011. The Mars Exploration Rover Opportunity has driven about 45 kilometers since it touched down, right? So one flight is going to cover the distance Curiosity traveled since touchdown. 2 or 3 flights will cover what Opportunity drove since its touchdown. All right, so as we get better range numbers and we start to incorporate more and more kind of higher order performance models in the performance codes, right, that's going to modify the or give us a more precise number on the actual range that we can fly in the aircraft. So all of the flight and science operations are paced by the day-night cycle on Titan, right? So a Titan day at TSOL is just under 16 Earth days. Okay, that means that we are out of contact with Earth for about 9 days at a time. The output from the MMRTG is between 70 watts and 100 watts. We use that to recharge the flight battery. Okay, and it's the flight battery that we use to actually do the flying on Titan. Right. So while we're at a daytime configuration, that's when we do our flight. And then we do some science while it's daytime, and during the nights, during Titan night, when we can't communicate with Earth anyway, right? That's when we're busy doing all the recharging and with the occasional nighttime science activity. Okay, so I can give a brief overview about navigation. Okay, we have sort of the typical stuff, right? IMU, right? Onboard the vehicle, we've got navigation cameras, a radar, and a LiDAR. The main job of the LiDAR is obstacle detection during landing, and all of the navigation is done using navigation cameras. And so it's optical navigation, two flavors of optical navigation happen. One of them is optical velocimetry, right? So that's during the flight phase. And then there's the position and mapping mode when we're closer to a hover mode for the aircraft. And so this you can see actually in one of the papers that came out a couple of years ago. More details on this and will get published later as well, right? So here we're correlating images, from one image to the next to figure out how far we've flown from one image to another. Another thing that we end up doing is during flight, we'll save images that have good feature content to a database, right? That's our map database. And as we fly, we'll be able to and revisit places we can cross-correlate the images with what we're calling the breadcrumbs, right? The sort of navigation and transit cycle is a sort of 2 steps forward, 1 step back process, right? Where we take off, we fly, we explore a landing site that we intend to visit on the next flight cycle, and then we fly back and land at a previously explored landing site. The reason for this operation, even though, right, we obviously won't be going nearly as far on a given flight, but it means that we are always going to have an explored and known to be safe landing site within flight range at all times. Okay, so it's a way of reducing the risk of our exploring flight. It also means that we're able to revisit places as we go, right? So we'll be able to use the, what they call the breadcrumbs that we generate during flight, so that will help us reduce our navigation error as we go. Okay, so I'd mentioned that there's plenty of Earth analogs here, right? So this is a image of the Namib Desert, and we'll be able to do flights here on Earth to validate and verify and cross-check performance of all of our navigation algorithms. And those flights, some of those flights have already happened, not in Namibia, but sort of nearby. And so we'll be doing a lot of flight testing here on Earth. At Penn State, we've built this vehicle, Firefly 45. It's a 45% scale test bed of Dragonfly. There's also a 66% scale vehicle that's also in the works. This vehicle is actually carried and flown with the navigation system, the visual navigation system that'll be going to Titan as well. And then I'm going to close with, this is actually, it's an artist impression video, right? But it's a neat video of what I think is going to be one of the coolest and most fun things that's going to happen. And that, actually, let me assume I can get this video going. Which is the entry descent, right? So we're descending under the parachutes. We'll see the legs unfold. We achieve lock on the ground with the radar. We spin out the lower rotors, and then we exit from the vehicle, and we become a powered flight vehicle. So I mentioned, right, there's lots and lots of us involved. This group of about 100 or so people standing here, this is the Phase A team, right? And so now we're into growing this group of folks enormously as we go. So thanks to everyone for your attention. I'll stop the screen share, and hopefully my picture appears again. And I'm happy to take questions.
All right, well, thank you very much, Jack. Very, very interesting work. We've got time for just a couple questions here. Let's see, we've got the first one is, how do you, on the Earth testing, how do you plan to account for the gravity and atmosphere differences?
Yeah, so we've designed the scaled vehicles so that they fly or hover at roughly the same thrust coefficient as the vehicle on Titan will be flying in, right? So we're not going to be flying at full weight on Earth. We'll be flying semi-low. So we're scaling disk loading and Froude number. The way that we intend to account for the fact that, you know, the sort of ratio of you know, that inertia is so different. So we can scale inertia on the vehicle here on Earth by placing weight appropriately. And then we can also go and scale the kind of artificially scale things by playing with the time constants on some of the control loops on the vehicle.
Let's see, another question is, do you know much about the winds that you'll experience and disturbances? I guess you mentioned they're not very high, so hopefully that's not a big challenge. And I guess with that, is there any danger of the dunes? Are they pretty stable, or is there shifting, you know, as you scout out a site, is that going to change over time?
Yeah, so we've got data from Huygens and also radar data that suggests that winds on Titan are well below 2 meters per second. With 1 meter per second be like 1 meter per second being a pretty windy day. We have been running large eddy simulations of winds over Titan dune fields to get an idea of what the turbulence characteristics are likely to be like. You do see some turbulence, but it's all kind of very slow, gradual motions of things. So we don't, and you know, simulations of the, you know, high order simulations of the vehicle flying in those kinds of environments really don't show any significant challenges to the flight control system.
All right, great. Well, unfortunately, I think we do need to move on to the next speaker. So we appreciate very much that. Hopefully that there'll still be opportunities for people to reach out and ask questions, perhaps later on. But we are going to stick with the schedule and move on to the next speaker at this time. So thank you again, Jack.
Thanks, and anyone can contact me anytime with questions.
Let's